right, so section 1, we had talked about transformations and we went over the different types. So we talked about translations, reflections, and then we talked about stretching and compressing. So we're still going to do a little bit of that in this section, but in this section we're going to talk about parent functions. So I said that when you're doing transformations, you're basically taking a graph or points and you're moving it somewhere else within the coordinate plane. So we have these things called parent functions. And parent functions are kind of like the original graph for a specific function, whether it be just a plain line, like a quadratic equation, or really any type of other equation out there that we could possibly ever run into. There's different types of functions, so this chart kind of summarizes the different functions, but the parent function is considered to be like the original graph. It's the simplest one, and it kind of is what everything else is based off of. So everything is going to look like the parent graph, meaning it has the same shape or same kind of structure to it, but it might change a little bit in where it's at on the graph. So it gets pushed left or right or up or down. It gets stretched or it gets compressed or stuff like that. So in this chart, these are kind of the main functions that we're going to be talking about and working with in the next couple of sections when we're doing transformations on our parent functions. So the first one is called the constant, and that's just when you have horizontal lines. And we kind of talked a little bit about that when we went over slope a while ago, where if you have no slope, it's just a straight flat line. There's no up or down at all. Now linear, this is what we've been dealing with like yesterday and when we were graphing lines using slope-intercept form. All of those are considered linear graphs because they're all straight lines. Okay, but the original, so like the parent function, goes through 0, 0, and it goes up positively. So if you had a slope that was like negative instead, chances are then that you took that parent graph and you reflected it. You just kind of flipped it over to the other side. Quadratic, that's when you have something with an x squared in your equation. And all quadratic equations kind of look like this curved U. And it goes up on both sides. And it's perfectly spaced. So if there's a point on the left side of the graph, there should be a point on the right side that matches up exactly the same. Next would be the cubic function. So this one looks a little bit different because you've got part of it going up. So you've got part of it going up into quadrant 1. And then you've got this part going down into quadrant 3. You don't remember what your quadrants are. They make up the 4 like places in your coordinate plane. You start in the top right corner, that's number 1, and then you go around counterclockwise, so it kind of makes like a C. 1, 2, 3, 4. Last one is the square root function. That one's only contained inside of quadrant 1, because when we take the square root of numbers, we want those numbers in there to be positive. We can't graph the square roots of negative numbers. It doesn't work that way. So these would be all of the parent functions. These would be the simplest form of all of these graphs. What we're going to do today, what I'm going to show you some examples of, is what happens if we start doing some of those transformations that we talked about yesterday. If I start moving it to the left, if I start moving it up or down, if I reflect it, if I do things like that, how does it affect the way that the graph looks? Now, if you have a quadratic equation to start with, when you go to graph a new one, it should still be a quadratic equation. So the shape shouldn't change. Like you shouldn't start with a square root function and all of a sudden it becomes a straight line. Okay, so it should still have like the same shape and same features. It's just maybe going to be in a different spot on the graph. So what we're going to do is look at some examples, and they're going to ask us to first like kind of state what happened to the graph, so what changed, what caused the parent function to be moved, or what's the transformation that's occurring. And then we're going to graph both the parent function and the new graph. So this first one we have g of x equals x plus 5. So when I look at it, the equation here, I just have plain x. So if I go back up to that chart that I gave you guys in your packet, the second one that says linear, that has that f of x equals x. So that's when we have just a plain x, because the next ones have x squared, x to the third, and then the square root of x. So you just want to kind of match it to which function we think it belongs to up above. So this would be an example of a linear function. It's kind of in that y equals mx plus b form. So I'm going to go ahead and write that the parent graph for this one is going to be the linear. So now let's talk about the transformation, like what happened to this graph. So when we see plus 5 added to the x, that's the piece that's different from the parent, because the parent would just be x. This has plus 5 added to it. So when it's got the plus sign at the end, that means that it's going to be moving it up. If it was a minus 5, that would move it down. So I'm going to say because it's plus 5, that it's going to go up 5 for my transformation. So now we need to graph it. The easiest way to graph these is to first just kind of graph the original function, so the parent, and then take all those points and just move them like you guys did yesterday, where you had a point originally, and then when you guys had to graph it, you just kind of moved it following the directions that they gave you. So for the original graph, for the linear function, if I think about making like a t-chart for x and y, so I'm looking at this g of x equals x. Remember, g of x is just a fancy way of saying y. So this is really the equation y equals x here. I'm going to put in some numbers for x, and I do some negatives and some positives, and I do this for all of them. So -2, -1, 0, 1, and 2. For this one, because it's linear, whatever you put into x, y is going to equal the exact same thing, because my equation says like y equals x, or g of x equals x. So when I put in -2 for x, I get -2 for y. -1 for x is going to be -1 for y, and so on. So 0, 1, and 2. So now I'm going to graph, and you guys should have a graph already in your packet that you can use. So I'm going to plot these points. This would be the original function. So this would be called the parent function. So we have 0, 0, 1, 1, 2, 2, -1, -1, -2, -2. So you should see that this is going through the origin. It looks exactly like the parent function that I have up in that chart up above that we talked about at the beginning. Grab something so you can draw your straight line. Again, if you have like your lunch card or something like that, that works really well. If you don't have like a ruler or something on you. Okay, so that's the parent function. Now I need to graph the new one that moved up 5. So in order to do that, I've got these points on my graph. I'm just going to take each point and I'm just going to go up 1, 2, 3, 4, 5 and draw a new point there. So if I start at 0, 0, I'm just going to go up to 5 and draw a new point. And do the same with those other ones. It should look the exact same. It should still be a straight line. It shouldn't all of a sudden have points that have completely veered off or gone into a different area. They should still form that straight line. It should look the exact same. It's just you've taken that entire parent function and you've pushed it up 5 units. And then draw that line again. If you need to, you can label them. So the one that I put in the green is the parent, and the one that I put in blue is the transformation. Okay, let's look at another one. So number 2, we have g of x equals x squared plus 5. So can you guys tell me what you think would be the parent graph? So go back up to your chart there. Look at what the equation says. Look at those names and tell me if you think it's constant, linear, quadratic, cubic, or square root. Which one do you guys think it would be? Quadratic, because it's got an x squared involved. Okay? So the parent function here is going to be the quadratic. Because we would have g of x equals x squared if it was the quadratic one. Now this one also has the plus 5, just like number 1 did. So what did we say that meant? Good, up 5. So the transformation is going to be the same for this graph. Still going to be up 5. The only difference now is the way our graph is going to look. Instead of having a straight line, this one's going to be quadratic. So it's going to be like that curved U shape. So let's talk about what this one looks like. So again, I'm going to make a T-chart for my original graph. And the nice thing is that once you guys have these original charts taken care of for like your linear, your quadratic, your cubic, it's the same every single time. And so if you know like what this chart should always look like for a quadratic graph, if you know what the numbers should be, then it should be easy then to find the new one because you just move those points around. So again, I'm going to do -2 to +2 into my x's here. And then again, we think up here, this is that g of x equals x squared. That's the same thing as y equals x squared. So when I take -2 and I square it, so I take -2 times -2, I get +4. -1 squared would be -1 times -1, which is going to be +1. 0 squared is going to be 0. And then we have 1 squared, which is going to be 1, 2 squared, which is going to be 4. With the quadratic graphs, they should form that pattern. Like we saw, it went 4, 1, 0, and then it went backwards, 1, 4. If I added 3's in there, -3 and +3 should both be 9. -4 and +4 should both be 16. So that pattern is going to repeat on both sides of that 0. All right, so now let's graph this one. Okay, I'm going to start with my parent graph. So those would be the points that I put in that T-chart. So -2, +4, -1, 1, 0, 0, 1, 1, and 2, 4. Since we knew that it was quadratic to start with, I said that it should form kind of that curved U or curved V shape, however you want to think about that. So when I go to graph this, you should be able to know if you did it right or wrong because it should look like the picture from up above. So I'm going to connect these dots. They're not going to be nice straight lines. They're going to be kind of curved. Do the best you can there. It doesn't have to be perfect. And then again, this one, the transformation is to move everything up 5. So all of those points, we're going to move them all up 5, just like we did on the last one. Okay, so I pushed them all up 5, and then I just draw that one in. So again, notice that it's the same graph. They both have that same shape. They're both the same size. All we did there is that we pushed it up. So if the number, like on number 1 and 2, we both had +5 added. So if it's addition, it's always going to be up. If it's subtraction, that means it's going to go down. But there are some cases when the number is like included in parentheses or like inside of the function itself, and that changes it just a little bit. So this one you had like the x and the x squared kind of by themselves, and then we had +5. So that moved it up or down. But if we look at number 3, you guys turn your page over. Notice on this one that the -2 is underneath the square root. So this is not going to move it down to. It would move it down to if it looked like this. If it was the square root of x and then minus 2, then it would move it down 2, okay? But the minus 2 is inside the square root sign. So this is not going to move it 2. This is actually going to move it either left or right, and we'll talk about how do you tell which way it goes. All right, so first of all, let's talk about what parent graph this comes from. So what do you guys think the parent function should be? Good, the square root function. Okay, so the square root function is like f of x equals the square root of x. Okay. Now this one's a little bit different because we have that minus 2 inside. So now let's talk about the transformation. So the transformation is underneath the radical sign, so it's included with the function. So we have to go either right or we go left. Now when we're doing right or left, you almost have to have like backwards thinking. A lot of times when we see minus, we think, okay, that means that we're going negative, so that means I should be going to the left. This is actually going to push the graph to the right. So that's why I said it's a little bit of that opposite thinking. You kind of just have to train your brain to understand that when it's underneath the square root or if it's included in the parentheses, that sign forces it to go the opposite direction than you think it's going to go. So this is going to go to the right too. So now let's make a t-chart for our square root function. So earlier I was saying when I made my charts, I always did -2, -1, 0, 1, and 2. This is like the only exception to that rule. I don't want to use negatives here because I don't want to have a negative underneath my square root sign. Because if you have a calculator and you're trying to do the math on your calculator, it will not do negative square roots for you. It'll give you an error message. Okay? We haven't talked about that yet. We'll get to that eventually. But I don't want us to have to worry about that right now. So I'm going to stick to positive numbers, but I'm also going to stick to numbers that I know I can find square roots of. So I don't have to worry about decimals. So I'm going to start with 0. And then think about those perfect squares we talked about at the beginning of the year. I wrote like that big list of numbers, and I said these are your perfect squares. So like the first one on that list was 4. And the next one was 9. You can do more if you'd like. You could then add 16 and 25 if you want, but just know like graphing those, 16 gets to be kind of big, and so does 25, because you'd have to go all the way over that many on your x. So 0, 4, and 9 are probably going to give us a good idea of what this graph looks like. Now, if I put those numbers into my square root function, I square root 0, and I square root 4, and I square root 9. So the square root of 0 is 0, square root of 4 is 2, square root of 9 would be 3. So these are the points again for your parent function. So 0, 0, 4, 2, 9, 3. My new graph, I take all those points, those 3 points that I graphed there, and I move them to the right 2. And then you just draw that same way. All right, so I want you guys to look at number 4. So number 4, right underneath this one. I'm going to give you a couple minutes, and I want you to try to do this one. Try to do as much as you can. So can you guys start by telling me what the parent function would be? Good, cubic. It's got that 3 exponent outside of the parentheses, and so that would go to the x, so it's like x to the third, which would be your cubic function. So the parent one would just be x to the third power. So let's talk about the transformation. This is similar to that last problem, number 3 that we did, where we had that minus 2. We said that went to the right 2. So what should this one do? Right 1. It's got minus 1 in there, so it's still going to go to the right. This is an example of when it's inside the parentheses. And that minus sign, again, just train your brain to think opposite there. If it's inside, we don't go left, we go right. Okay, so we go right 1. So when you guys made your T-chart, you can go back to doing -2, -1, 0, 1, and 2. The only ones that you only want to stick to positives was the square root function. So -2 to the third power, so -2 times -2 times -2 would get us a -8. -1 to the third power would be -1. 0 to the third would be 0. 1 to the third is 1. 2 to the third is +8. So notice for this one, like their quadratic graphs, they're the same numbers regardless if it's positive or negative that we're plugging in. Cubic is going to change a little bit because you've got the odd exponent. So if you take an odd number of negatives times themselves, you're going to still get a negative answer. So that's why this one's going to have kind of like a more of a tail on the one end. It's going to go down in one quadrant and go up in another. So then if we draw this graph, starting with the parent, you should have 0, 0, 1, 1, -1, -1. Then we have 2, 8. Way up there for me. So it goes up, and it's going to end up going down on the other side. And then for the transformation, we move all those points to the right one. And I would normally grab the other point, I just don't have room on my screen here. Okay, but they should look like that same kind of, almost like an S-type shape in there. It's just really loosely stretched. Okay, we've got one more here in our notes. So we have x plus 1 squared plus 4. So let's first figure out what would be the parent function for this. What do you guys think? Linear, quadratic, cubic, square root. Okay, quadratic. It's got the squared, so we would have an x squared in here. So we did a quadratic one earlier. This is going to be the parent function equals x squared just by itself. Let's talk about the transformation for this one. This has two pieces to it. It has a +1 and it has a +4. Which direction is the +1 going to make us go? Since it's inside the parentheses. If it's inside, remember that makes it go left or right. So this is going to go left 1. And what does the +4 do? Good, up 4. So we have that chart from number 2 that we did earlier. We can use that same chart for the parent function. I'm going to graph those same points from my parent function. Okay, and then for my new one, we go left 1, up 4. So again, they should look the same. Your graph should not change shape at all. It's just being pushed around on the graph.